Okay, today is Wednesday. The remaining topic I would cover is Monte Carlo simulation, but I'm ready to give a lecture today. But I kind of worry about the third example problem set, a 20 random variable problem. That's really the largest problem. And as I mentioned, as I go through procedure, gradient calculation, that's the key to a program. So last Monday, Yoon-Suk mentioned there is a function routine in the MATLAB, so I presume Yoon-Suk, Jun-Gun, and Yong-Hun, the group may be able to solve. But what's the status, Yoon-Suk, for gradient calculation? Tried it? Not tried it? Who cares? Select one. So have you tried for gradient calculation and problem?
The gradient function, but calculations. I just using the other function.
Which function? Differential function? So you're able to compute the gradient?
Yeah, I'm using that function to solve the example number 4.1.
For the what's the problem number? Example problem number 7.3, something like that. 7.3 in the Professor Du's notes. And example 7.3, this is 20, I thought. So 20 random variable.
Yeah, but in the example 7.3, there are too many variables, so I just using
7.2? Yeah, okay.
4.1.
Oh, 4 point, how many random variable? 2 random variable. 2 random variables you can compute by hand very easily to look inside the story. So it's very good for that. But if it's like a 3 random variable, then it's getting difficult to do by hand. So, but you try the 2 variable problem using the gradient subroutine in MATLAB? 한국말로 해봐. 응?
심볼 이용해서 적은 다음에 그 심볼을 이렇게 미분하는 걸로 이거.
그것도 gradient calculation 아니야?
근데 이제 제가 생각했던 처음에 그레디언트는 이제 바로 넣어서 하면 바로 이렇게 나올 줄 알았는데 그건 안 되고 값을 이렇게 X, Y, Z라고
Each component.
값을 이렇게 미분해서 거기에 이렇게 값 넣는 거는 제가 그래서 저번 시간에 이제 교수님께서 그 앞에서 민 밸류
그래, mean value.
그거를 이제 저는 그냥 퍼스트 오더로 한번 그냥 써봐서.
Okay, anybody tried example 7.3 for 20 random variable problem. Most kind of the difficult problem, the one area to overcome is a gradient calculation. Even author, the Professor Du, proposed the example problem, then he skipped all the middle part, then get the result out, because I'm pretty sure he used a canned program, which is available, commercially available. And I again forgot to bring the list of the commercial program to compute that. But, but this method, Monte Carlo method, which I'm going to give you insight this morning, that's trial and error. Some of you know that the Monte Carlo method in the probability and statistics, the course they should go through, which you might have to try something like 100,000 times or million times. But that method is somewhat popular because you don't need to compute the gradients and all that. So that may be another reason people use in many different fields, not just the structural reliability area, but in the finance and marketing and all that area, investment, stocks, the financial forecast, that's what they are using it. So I'm going to give you a lecture on that. Then you know the G function. You must know the G function. If you don't know the G function, of course you can't compute. Whatever the method you employ, you have difficulties. So Monte Carlo method I'm going to give you today. Then try out using Monte Carlo method like a problem 7.3. Okay? And last Monday, I give you so-called direct method without going through the transformation, which is mean value, the FORM, and directly you stick them in the X star, or the most probable point as mean value. Of course, it works pretty well for the performance function. If its nonlinearity is more there, like x cubed or x to the fourth power, sine, cosine, then you will see the problem. So this weekend, but that doesn't mean that don't just bother to try to get the gradient to solve using transformation from x to u space. Keep trying that. So I have no intention this semester to buy the commercial program. Structure reliability program is available, but not in Korea. That's what I know as of today. But this semester is concerned, it's too late to buy it, so I'm not going to bother to buy it for that. And try to solve. And using the MC Monte Carlo simulation, you can try out for such a 20 random variable problem. Once you set the G function, all you have to do is compute the G function maybe 1,000 times or 100,000 times, but it doesn't take really much time. When you use MATLAB wisely, then you can and solve. And this quarter, I also mentioned to you, term project, you must do it. Then Friday, I want you to really propose your term project, so proposal. So I want you to really come out to, we have a 3 group. So Friday, maybe sharing 10 to 15 minutes. You can present what you want to do. Then I'll return my decision by the email on Friday afternoon. Then I want you to give me the copy of your proposal. And if it's not quite acceptable as a term project, then I'll shrink as a small over the weekend project. Then we'll go through the final exam process. Okay? So after that, I don't have much to say on the structure reliability course. That's all I want to cover. So maybe solve a few additional problems, things like that. Okay? That's what we're going to do. Okay, Monte Carlo method. Monte Carlo method is this method, some people call it MCS method. It's very simple and straightforward. That's why people using in any field, any engineering and science field, first reference, of course, I want you to take a look at the choice book, this red cover book. A few pages is what you needed to read. Another area to understand better, I want you to look at the internet. If you type in the Monte Carlo simulation, in MATLAB, I think you have to type MATLAB. Then you will see a whole bunch of the internet address. Then you can select the few to take a look at the process, what people does it, and all that. So, and in addition, they have tons of actual lectures and all that. This is, take a look at the part of the YouTube. You access YouTube, right? So, YouTube. Then there is a short, like 2 minutes or 3 minutes, the video file. Then you can experience. It's a very pretty good. And Monte Carlo method. What's the target in structure? We are looking into the structure reliability. What's the target? Our target is to compute the probability of the failure. And the probability of the failure, as we quickly look at it, our concern is a probability such that this is less than equal to 0 again. The performance function less than equal to 0, then we are getting into the failure region. And this is like a multiple number of integration, and gx is less than equal to 0, then f(x) x dx. That's what we know. And this fx is a joint probability density function, and we know this gx is xi I is equal to 1 to all the way through n whatever that is. Then question arises, this is all joint probability, all tangled up together. So then we easily assume, so here is assume statistically independent. This assumption we brought in, remember? Among the random variable. Otherwise it's very difficult, almost impossible. For Monte Carlo simulation, of course, assume independent. First order reliability method is very nice because you approximate the g function as a straight line. And your concern, my concern, is at the MPP point. But for the second order, the reliability method, then you add additional term rather than 2 term in the Taylor series. Bring the third term, which is a quadratic term, square term, parabolas. Then it's getting very complex. Even Professor Du's, he wrote really well, but second order, he just mentioned, then didn't go through the computation. But choice book has quite a bit more. But it's not that clear like a first order, the reliability method. Anyway, here, statistically independent random variable, then all this equation set for this, you can simply multiply the probability density function of each random variable. That's what the simplicity come into picture. So you can say this is equal to fx1, fx2. You can simply get everything as fxn and dx1 all the way through dxn, one at a time. And as approximation, then another problem arises. Then this could follow the normal distribution. This follows normal. This follows the normal distribution. Then it's easy to compute. We can transform into U space very nicely because we can bring in the standard normal distribution function. But if this guy follow like different other than normal distribution, let's say this is a log normal distribution, this is like exponential distribution and so on, then it's a problem. You can't simplify it. So in that situation, then Monte Carlo method is powerful. Even if you have to really go through many, not the iteration, calculation. So this is a trial and error situation. So then, as you toss the coin, right? Flip the coin, and head and tail. So if you throw maybe 3 times, the probability that you can get the tail could be 1. You agree? If you throw the 3 times. But if you throw the 4 times, it could be all tail. Possibilities there. Sometimes, I don't know whether you have a chance to have a fun to bet, in the casino. I have some experience in the casino in California. And winter time we go out for ski. Not nowadays. I'm too old for that. But when I was up to about 60, every winter we go. Maybe some of you know Lake Tahoe, which is about 3-hour or 4-hour drive from San Francisco to the mountain. It's right at the Nevada and California borderline, and there's a casino. It's a really beautiful casino. But we had in the evening we go out. Not every night. You lose money. Set aside maybe $100, then play blackjack. Sometimes you win, most of the times you lose and come home. Then bet. Oh gosh, this time I lost. Next round I won. Next time I won. Then I feel, oh, I could bet more because I have a better chance. Then put all $100 out there. Then lost. So it's a probability to win. You throw the die, it has 1 to the 6 dots. So let's say if I get the single dot, let's say I win. What's the chance to have a single dot? 1/6. So if you throw first, you could have other than 1, twice other than 1, 3 times other than 1, all the way to 6 times, you could have other than 1. So, but if you throw 100 times, then it's getting closer to 1/6. Okay, so getting closer. So for complex G function, as you really do more experiment, then you have a better chance to get closer to the point, like MPP point, or very close to MPP point. You can say hit the jackpot, right, at MPP point. So this is what, but it's a very nice approach to get involved. So Monte Carlo simulation, maybe this afternoon, you can try for 7.3 problem, which is rather complex. So probability of the failure for structure reliability. If you look at the books, they have a variation from one point, another variation. Frankly, I don't care, the variation, but original principle, that's what I kept it, and that's the way I want to do. So that original scheme for Monte Carlo simulation applying to the structure reliability is denominator is capital N, total number of trier. Okay, total number of trier. Total number of computation. Then the numerator is N G X I less than equal to 0. You know the G function. And Xi is a trier set. Just it could be a number. Trier set. So Xi is you have a 20 random variable. You can pick out simply saying the trier 20 the variable set. And this N is, this is a number of trier which satisfies the G less than equal to 0. You could try 100 times. Okay, so the set is of course a random variable. So at the beginning you could use uniformly distributed random variable, equal chance. Okay, equal chance. Let's say your random variable could have a Young's modulus, and you could have length A or length B in the beam type structure as you see here. So this, we have a similar problem. So you could have a beam. This could be, for example, AB. Three random variable, let's say. Then this is 30 times 10 to the 6 psi. And X is something like 5 inches. B is like 10 inches. Simply just a beam. Okay. Then as you take this as a random variable, then you could say now this is a mean of it, right? Mean Young's modulus value. Plus, then you have to have a standard deviation for that. So standard deviation you could assign saying that this is 10 times 10 to the 5th power. And this is like 1 inch. This could be 2 inches, for example. Standard deviation. So then that becomes the random variable. So then you can compute, you can get so objective function you can call, but which is nothing but process to setting up the G function, as we have done. For example, deflection criteria, right? So deflection, when you have whatever the loading, uniform loading, or that, then you have, you could say this deflection is a critical issue to solve the problem. In our problem number 7.2, as I recall, giving the allowable, as you have done too, allowable deformation is something like a 3" or something like that. So, okay, G function is something like a 3" maximum, and minus what? Actual. Let's say just a function of f, a, b, e, actual deformation. You can compute. You can get the equation set. Okay, you can derive the deformation as a function of this, plus of course you have a length and all that. Right? Then you can get the G function now. So you have a G function. So as a function, you have a G function. Then now you have pick out. It's based on the random variate. Random. You pick out the random. How to pick out the random? That's what I'm going to show you. You can pick out the random, assuming like a uniform distribution for each random variable, or you can assume normal, or you can assume normal, log normal, exponential, if you can justify it. Then you select the random variable for trier. Then you will have a set of the random variable. If you want to try 100 times, you have 100 set of random variable. Then you stick them in. You compute the G function. Then G function, you try the 100. Then not all, you don't expect all 100 trier meet this criteria, less than equal to 0. Maybe 30. Maybe out of 100, this criteria is met 30 times out of 100. Okay? Then your probability of the failure is 0.3. 0.3. But just a quick example here, which is for structure reliability is concerned terrible. That's not totally not acceptable. So that's what you have to compute. Then in the process to compute how to pick out the random variable, random trier set, xi. How are you going to pick out the trier set? That's the questionable. So that's what you call if you look at the choice book, it shows pretty nicely using so-called the inverse transformation method. I don't know why they put all that name, but it's pretty nice set. Let's just put for a quadrant. Let's say xi, one trier value out of 3 in this case, follow the exponential probability density function, then I can say, okay, exponential. So this is x, this is of course fx. Exponential is naturally going like that. If it is a normal, it should go like this. If it's a uniform distribution, it comes straight out like that. But let's say generally, just to draw the exponential. Then in this quadrant, I can say, okay, I'm going to get the cumulative distribution function, which is nothing but summation, then it's getting too close to 0, then it could go like this. This is approach to what? Approach to the 1. The range, always range of cumulative distribution function is 0 to 1. Or it could be, if it's a uniform distribution, it could be the linear straight line variation, right? Okay, that's good. So if I pick out some value xi, then I can say, okay, it related to this number. If I put these guys in, this relate to the value between 0 and 1. Between 0 and 1. It's a random number. You need to generate random number. Then you can, once you generate the random number, which is between 0 and 1, to compute the trier value for Young's modulus, what I can do is the mean value plus the random number multiplied by that number, which is the variation. You can add a plus and minus if you want to, right? Then that's a trier, the value. Okay, so this is 0 to 1. Then to complete the inverse process, so I'm going to draw in the left quadrant, 2 quadrant. I'm gonna do, you have to, this is like FU, U, from 0, this is U. This is uniform, like a uniform distribution, uniform density function on the left quadrant, really to any value it could be. So here I could draw just for linear. This is a 45-degree line. It's a process, it's nothing. So here, if I could put this guy could be the 1, if this is from 0 to 1. And now for the xi, okay, for the xi, it pick out that value. This is a 45-degree angle. Then now I can drop down, it corresponded to 0 to 1. So this is, I'm going to call the UI. So whether pick out the UI or that value is really same. The value, random value between 0 and 1, which follows the exponential distributions. Okay? So you can pick out the, that value. So in terms of equation, xi become the ui. Very straight. So ui is equal to fx inverse, xi is inverse ui. That's why it's called the inverse, the transformation. In the MATLAB, if you go into land D, I think, land D variable or function is a function, and it's open parenthesis. If this is a 1, it will pick out the random number between 0 and 1. If you type this, it will pick out, every time you type this, it pick out the random number between 0 and 1. Then you can multiply this, for example, multiply to this guy, then add mu x, random number ui. This is random number. Then you can have a trier. For example, you can have a trier number. You can pick out the same way. You can pick out the same way. Then you have a one set as a trier value. Apply to performance function. Then if that performance function is in failure region, then you count that as a 1. Then you compute, the second set, you can try. Then if it's in the safe region, that's a fail, right? Then you can keep adding, then you can divide it by number of trier. Then that's a probability of the failure. You follow the theme, right? That's about it. There is no gradient calculations and all that. And what happens if you have a normal distribution? What do you expect? You have you could have whatever that is. I'm going to cut as just a positive. So in this case, it's going to be similar, but degree of the curvature would be different. Then the same approach. If you want to have this, you compute, you calculate. Then you can throw all the way in. Then you can compute. Then you can use that as a random, the variable. But if you, as far as I know, if you pick out the RAND, R-A-N-D, in MATLAB, I think that's based on the uniform distribution. That's what my understanding is. And you may check out the MATLAB, to look at how to generate then for the other than uniform distributions. check out. But there is some merit to assign the probability function, because some performance function is concerned is more clear what kind of a probability density function you would use. For example, like a hit and miss problem. Hit and miss problem, you could see the target. This is like the area you want to hit in the target practice. And the whole thing is, this is like a 1, this is like 1, and this is like 0.5 is too much, 0.5. Then you stand from some distance away, then you shoot 100 times. Then you can pick out the random trier value based on the equal chance, uniform distribution. Pick out, then you could hit any place within 1 square meters, 1 square centimeters. Then question is it good? Random variable based on the uniform distribution? Maybe not, because there are chances to it all other area, but normal distribution may fit well because it has the peak at the middle with a small the standard deviation. If it's a uniform, you could, if you try many times, result would be very close to each other, like 100 times or 10,000 times. The result would be very close whether you use the uniform or normal. But if you try only 100 times, then if you assign the normal distribution rather than uniform, would be better. Well, what happened? Your area of concern is that there was the probability to hit that area. And what about the area you're concerning is that area? Maybe exponential distribution would be better. So you need a little bit thinking, even if Monte Carlo method, which is really randomly generate the result, but still before you attack, then think a little bit, then try. But if you try many times, regardless of the probability function you assign to the trier value would be the same. This is about all the basic function. If you look at like a choice book, other book, there is a crude Monte Carlo approach. Same. All the basic equation is this for structure failure. Evaluate the G function without the gradient calculation, without knowing MPP, without using the mean value FORM. It's a straight computation. So try this, okay? Then try this using example 7.3, 그죠? Then 7.3 and 7.2 also. 7.2, you have a small number of the random variable. Then bring on Friday, let's discuss about that. And Friday, are you going to be ready to give a talk and proposal? Friday, we'll do that. Then also problem number 7.2 and 7.3. Then if it's too much, then we'll do it next week. Okay, so I'll see you Friday. Any questions on Monte Carlo? Okay.